All right, multiple choice for lesson 27. Problem one, you're trying to open a stuck door with pulling on the doorknob. Does it change the torque if you tie a rope to the door and pull the same way? So that same way is important. So if we have our pivot point there, we've got our door coming out, and say we've got a doorknob on the end. We're going to try and pull on that doorknob with just pulling directly on the doorknob, or maybe we try a string to the doorknob and we're going to pull it out, and then we're going to pull on the string instead with the same amount of force. So in both cases, our actually we'll start with this. Torque is R cross F, and they are all vectors there. So we need to know the radius and then the magnitude and direction of the force. So our radius for the door is going to be there. Both cases, the force is being pulled at the same radius from the doorknob because that string is being pulled in the same direction, in the same way, with the same force. So we have our radius, we have our F pull, and if we really take a look at this, we want to know the angle between them is both the same in both cases there. So if the force of the pull is the same and it's in the same direction, we do not have a change in the torque if we use a string. All right, problem two. We have a bolt stuck on an aircraft engine, so we're trying to pull it off with two different size wrenches. So if we diagram this again here, we've got wrench one, and we have wrench two, which is twice as long, and we're trying to look at, say, force one and compare that to force 2. How do they actually compare to one another? We know they have the same torque. So once again, we're looking at torque is R cross F. And so if we look at 1 and 2, we'll write it this way. So R1, we know we've got some, let's label this really quick. We've got R here, and then we know it's twice as long, so that just means we've got R again out to the edge, because one's 15, the other's 30 for the length of those wrenches. So for problem one, wrench one, we've got our torque is going to be R crossed with some F, and we know that it's the same torque. So this one has to be 2R times some multiple of F. And so let's just call that X. We want to know what our X is, how many multiples of that force we have. So if we know that it's twice the radius, then that means that the force has to be 1/2 in order to give us the same torque. So if we have the R's are going to cancel, the F's are going to cancel, and that leaves us with 1 has to equal 2 times X. X has to equal 1/2. So we know that the new force has to be half as much as that old force. All right, so problem 3 here, we'll zoom in so we can actually look straight at these wrenches. In this scenario, we should have a wrench. We have a rod that we can apply to the end of the wrench, and then in all cases, we're applying the same magnitude of force. The wrenches are the same length, and the rods are all the same length for each of these scenarios. So once again, we're looking for torque. We want to know which one has the greatest torque, and torque is equal to R cross F. And another way to say that is R F sine of theta if we're applying that force at some angle, and it's the angle between the force and the radius. So in each of these cases, we've got some R. Well, let's take a look at these here. So in case one, we've got the torque is going to equal the radius of the wrench. So if we just draw that up here, that's the radius, and then we have our force coming off of that, and if we draw the angle between those two, that's going to be 90 degrees. So we have the radius of the wrench times our force times the sine of 90, which is 1. So there's wrench 1. Scenario 2, we've got the radius of the wrench here, and then we also have the radius of the rod. So RW plus R rod, and then we have our force once again coming off at a 90-degree angle there. So if we write this out, torque is going to equal to RW plus R rod, all that times our force, and then we have the sine of 90, so which is 1. And then we go wrench 3. In this case, we've got our wrench, and then we have force coming off that way. The angle between them this time, we do have some angle, so torque is going to be our wrench times the force times the sine of whatever that angle is going to be. So we know that's going to be less than just RF. And then for wrench 4, once again, we've got our wrench coming up, and then the force is being applied perpendicular to that end and not extending out any farther. So our torque is going to be our wrench times the force again. So if we look at all of our scenarios, we can see that scenario 2 is actually the largest torque. So that answers that question. All right, for our last problem here, problem 6, we're looking for rotational inertia, that moment of inertia that we're trying to find. So we're trying to find I. And if you look on your equation sheet, you should see something that looks similar to this. Those flat plates are approximately similar to a book, where the dimensions are far greater in 2 of the dimensions than that third one. So if we take a look at our books here, we'll just label this as A. This side is going to be B, just so that it matches up over here, and we're going to compare A, B, and C. So if we look at book A, we know that I is going to resemble which of these? Well, it looks much closer to this bottom one than the top one, because we're spinning it around one of those longitudinal axes. So in this case, we have 1/12 M, and the axis is going through the long side of the book, here. So that would be A squared. All right, for B, we're also looking for I. So in this case, if we look, it would be similar to this, except for our axis is now out of this, our rotational axis is now out of the side of the book. So an analogous I, or moment of inertia, would be 1/12 mb squared, because we're rotating it around the side of length B. And then C here, this one we're actually rotating through the top of the book, so that one is actually looks more like this particular I up here. So in this case, I is going to be 1/12 m, and then we have A squared plus B squared, and so our book that has the highest rotational inertia, if we compare all of these, is going to be C with that a squared plus b squared.